Good afternoon, dear student, and welcome once again to this second edition of our functional analysis class. Unfortunately, it was not a scheduled class, but as I told you, I can post videos or recording from time to time just to put you on track. Yeah, on the rail. I thought it would be important for me to post the first tutorial, the time for you to assimilate the concept of sigma algebra, what's a measure, what's a measurable, mapping or function. In a sense, measure theory and integration is a semester course. So I'm not expecting you to know everything, it's just to have an idea, right? Just to have an idea, particularly to understand what is an LP space. The basic understanding is very important, and the theory can be explained to you in 1 hour, but I don't just want to come and browse over the concept of measure theory, but I want you to feel it by solving a few problems. You don't need to know all of everything, but just to understand the general idea so that it will not appear to you as something you have never heard, right? And that's something I cover with the statistics student during the first semester in the stochastic processes. And I told her, no, you at least you're a mathematician, they are statisticians, true, they use it because when you talk about expectation, it's an integral. You cannot talk about expectation without talking of integral. And expectation is an integral, so that's measure theory. That's why they go through measure theory. And a random variable is a measurable function, so that's why they go through all these things. But you, a mathematician, you don't even have a clue. It doesn't make sense that a statistician will stand next to you and start talking about stochastic processes where they use the theory of measure and integration. And you are a mathematician. You don't have a clue. It's a shame. That's why I said, no, let me introduce a small paragraph. And actually, it's a matrix space, right? It's supposed to be part of the matrix space. And I remember the previous years, in some example, I used L2. L2 to student, I just say, okay, it's the set of a square integrable function. Yeah, they were just here like that, but they don't really know what it is. So that's why it's really important to have an idea, right? Okay, so what I prepare, you can check on the same platform. I will upload later on the e-learning platform, but here on the Microsoft Teams platform, I uploaded the first tutorial. It's exactly on sigma algebra measure immeasurable mapping or maps. Okay, so this being said, let me start with the first thing. I think maximum 30 minutes I will be done. I just want to solve a problem for you to understand the concept more and more. So I'm going to go through the first question of the tutorial. And that question, let me share, I can at least share that question with you. This is the question. Sorry, please change this on your tutorial sheet. This is FAN 802, not 1. I realized it when it was when I already printed. It's fine. I already uploaded, so you can change it, right? Okay. So now here we are given a set, what I call last time A or E. Here we are calling it omega, right? Omega, of course, omega, because in probability we work with omega, and then we describe our experiment over omega, right? Because this is omega, the set of all possible outcomes, and then sigma algebra, in fact, will be a partial knowledge of the outcome, right? And you can see that elements of a sigma algebra, in fact, are what we call events. They are events. So when you say an event in probability, in fact, it's a measurable set. A set to which you can apply probability, because probability in itself is a measure. Okay, so we'll come to that. So when you talk about measure theory probability, they are really intertwined, if I can say. And you can see that if you say probability of omega or the measure of omega is 1, it is 1. So what makes the difference between a simple measure and a probability is that for a probability is a measure whose value, I mean, when I say whose value, I mean the value of the set of all possible outcomes, which is omega. The measure of omega is 1, whereas when it's different from 1, you don't say it's a probability, right? So anything that you do in probability of, I mean, in measure theory applies to probability. The difference is that P omega is 1, or mu, if mu is your measure, mu of omega is different from 1 for an arbitrary measure. But when mu of omega, that's the measure of omega, is 1, you call that measure a probability, full stop. So the rest is there. Okay, so now we are given 3, you can see that all these, if you look at the elements of F, calligraphic F, calligraphic G, calligraphic H, when you look at all the elements, you can see that they are all subset of omega, right? Subset of omega. And we know that the power set, the number of elements of the power set here will be 16, because 2 to the power of 4 is 16. Now, if you count this element, you see that they are subset of the power set, because if you count 1, 2, 3, 4, 5, 6, 7, 8, that's half what is supposed to be to form the power set. So you can see that all these are subset of the power set. So all the elements, I mean, the cardinality of each one is 8. 1, 2, 3, 4, 5, 6, 7, 8. Similarly, here is 8. You see they're all aligned, so it's 8, 8, 8, 8. Okay, so these are not the trivial whatsoever. First of all, let us, they are subset, but we are not sure whether they are sigma algebra or not. Because for them to be sigma algebra, we need to check that the condition, I mean, the properties of sigma algebra are satisfied. Then we know that it's a sigma algebra. The property or axiom, right? Call them also axiom. So the 3s are given, and now we are asked to decide which of the following collection is or are sigma algebras, and the one that are not. And for that, we can also justify why they are or they are not sigma algebras. Okay, now if you look at the very first one. If you look at the very first one, the first definition, we can see that we have omega. Omega, the empty set is in all of them. And omega itself, which is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, they are also there. The 2 are there. But is it enough? I don't think so. It's not enough to conclude whether it is a sigma algebra or not. It's not enough. So we need to check those the various properties. So we know already that omega, the empty set and omega are both there. But now, if we take if we take an arbitrary element, there is is complement still in the set. So we can do that. To do that, we check for each one. But if we can spot directly that something from the definition is not satisfied, we just pinpoint it and say that, okay, this condition is not satisfied, therefore it's not sigma algebra. You stop there. You don't need to check everything. It's like a counter example. Good. Now let us look at the first one. The complement, because when you say complement, is with respect to the base class. That is with respect to omega, because omega is our base class. It's like X. Yesterday we talked about X. X was our base set. So when you say complement, is with respect to omega. Okay, now if I take 1 complement omega, it is this one. 2, 3, 4. If I take 3 complement, I just come here, I remove 3. It will be 1, 2, 4. 1, 2, 4 is here. This one. Now, if I take 1, 3 complement, 1, 3 complement should be 2, 4. 2, 4 also is here. Now, if you take 2, 4 complement, it will be 1, 3, which is the complement of the other one. So now, what if I take 1, 2, 4 complement? 1, 2, 4 complement is just the singleton 3, which is here. I think this also 2, 3, 4 complement is the singleton 1. And finally, the complement of this, which is omega, the complement of omega is the MC set. So we can already say that the property that states that for any element here, this complement is still in, that property is satisfied. Now, what if we take an arbitrary union of elements here? In fact, it's countable a countable union of element of F. Is it still there? Countable union means that you take an countable, that is something that you can count. You take the union as many as you want. Now, if you take the union of all of them, it will give you omega. Now, if you take a union of particular ones, let's say we take union these two, it will give us this one. We take the union of these two, it will still give us this. We take the union of this and that, it will still give us this. We take the union of this and that, it will still give us that. Now, if you take the union of these two, it gives us omega because it will be 1, 2, 3, 4. Right. Now, if you take the union of this and that, it will be 1, 2, 4. 1, 2, 4, which is this one again, because it's a subset, right? Now, if you take this and that, it will give us this. Right? So you can see that if we take countable union, so we can conclude that the first one is a sigma algebra. This one, oh, okay, F is a sigma algebra. Everything is correct with F. But for the remaining two, it will not work, right? Why will it not work? Okay, now let's look at the complement. If we take the complement of what? Okay, let's look directly. If I take the complement of 1, it will be 2, 3, 4, which is here, no problem. The complement of 2 will be 1, 3, 4, which is here, 1, 3, 4. Now, what is the complement of 1, 3? 1, 3, it will be 2, 4. Is 2, 4 there? No. So 2, 4 is not here. 2, 4 is not here, which is in fact this one. You can see 2, 4 is here. But this 2, 4 is no longer there. But in place of 2, 4, 3, 4 has been replaced. By replacing 2, 4 with 3, 4 messes everything. You see? What did I say? I say 1, 3, right? 1, 3. So if you take this out, you will be left with 2, 4. And you can see that 2, 4 is not here. So you stop just there. You say that G, calligraphic G, is not a sigma algebra. Why? Because the complement of 1, 3, which is 2, 4, is not an element of this. You stop there. You don't need to proceed to other element or countable union. No, stop there, and it's not. It's not there, so it's not a sigma algebra. Now, if you come here, compared to the other ones, you can see that things have changed here. If you look, let's look at the complement of 1, 4 also and see. If I look at 1, 4, it will be 2, 3, which is here, okay? 1, 4, 2, 3. And what is the 1, 2, 3? Okay, it's the complement of 4. And 1, 4, the complement of 1, 4 is 2, 3. 2, 3 is also here. And if I say complement of 2, 3, it will be 1, 4. Okay, now what is the complement of 1, 2, 3? The complement of 1, 2, 3 is 3. No, sorry, it's 4. 1, 2, 3, its complement is 4, which is here. Okay, it's already there. And the complement of this 2, 3, 4. 2, 3, 4 will be the singleton one, which is here. Good. And the complement of omega is the empty set. So that one is okay. Now, if I take the union, these two, the union will give this one. If I take 1, 2, 3, is there. If I take 1, 2, 3, 4, these two, if I take the union, it will be this one. If I take the union, okay, this is included, so if I take the union, it will still be there. Now, if I take 4 and 2, 3, the union will be 2, 3, 4, 2, 3, 4, which is here. Now, if I take, okay, this is contained, so if I take the union, it will be this one. Okay, so apparently, because if you keep doing that, I think, okay, so these two, F and H, are both sigma algebras. So you can check that yourself. So the only one that is not a sigma algebra is G, calligraphic G. The rest are sigma algebras. Interesting. Now, here, we are given a function, f defined from omega to r. And that function is defined for each element f in omega. F of n is -1 to the n. Now we have to decide whether f is measurable or not with respect to the sigma algebra defined in question 1. So we have two sigma algebras here. We have f and we have h, calligraphic f, calligraphic. So these are the only two. We cannot use g because we know that g is not a sigma algebra. So for this problem, so what we will need to do is to consider omega and couple with f and check if it's measurable. And similarly, we can take the second sigma algebra and see if omega coupled with h, calligraphic h, is also a sigma algebra. It's a measurable function. Now, I will only do that for the first one, f. I will do that for f. You will be able to do the same for h. Now, if I take the case of calligraphic f with this function, the first thing to do, let me open a new window where I want to write. Okay, so let me open. Oh, sorry. No, this one will open. That's not what I want. Yeah. I don't want this. I don't want this one. What I want. Yesterday was okay. I don't know. Maybe this one. Yeah, I think it's this one. Okay, so okay, let me quickly write. Calligraphic F. We have the empty set. We have the singleton 1, the singleton 3, then 1, 3, 2, 4, 1, 2, 4, 2, 3, 4, and finally omega. One, two, three, four, five, six, seven, eight. Okay, they are all there. Now we have our function f from omega. So for the first case, I would just consider this measurable space. This is a measurable space because this is sigma algebra on that. So this is called measurable space. It's measurable, meaning that we can define a measure in that. Okay, now here in R, but this is a real value function, right? And remember, we define what we call the Borel sigma algebra, because you cannot use this without the sigma algebra defined on R or over R. So if you use R, remember R will always be coupled with its natural sigma algebra, which is the Borel sigma algebra. So now we want to check if this with F, if I change F, the next will be H, calligraphic H. We want to know whether this is measurable. Now, okay, since F of n, if I take n here, n can be any element of omega, that is 1, 2, 3, 0, 1, sorry, 1, 2, 3, 4. So for each of these, I know already that it will be negative 1 when n is one of these. One, 3. 1 or 3. And now this will be 1. When n is one of these, 2 or 4. So this is the, F. Okay, so that's how we define our F. And remember the definition of measurable. F is measurable, or F measurable. You can say measurable or F measurable. When you say F measurable, means that with respect to F is calligraphic F measurable if for any element here, for any A of the Borel sigma algebra of R, the pre-image of A is in F. So that's the definition of a measurable function, or F measurable. So that's what it means. So when you say for any. Now, what is the Borel-Sigma algebra? The Borel-Sigma algebra is, anyway, anything in the Borel-Sigma algebra is any kind of interval that you can imagine. Any kind of interval in R that you can imagine will be the Borel, it will be an element of the that Borel-Sigma algebra. Any. Okay, now, because we say for any, for any. For any. Now, if I take an element, no, let's for instance, let A be of the following form, because element here can be of many forms. It can be, you can take negative infinity, a certain A, like this, right? Or you can take an interval A, B, so it's up to you. So let us take this one. Let us just concentrate on this one, because this one is enough to represent that, right? You can take this, where A is a real number. It's a real number. A is a real number. And we can also even take this A to be infinity, right? If I put the bar here to say that I can take A to the infinity. Now, if A is infinity, this will be R, right? Because remember that in a sigma algebra, the underlying set, which is R, is contained there. So I can take this A to be R, because R is an element of BR. So if it is R, if A is R, in R you get both -1 and 1. It will be both -1 and 1. So if you have both -1 and 1, because they are both elements of R, what will be the pre-image? The pre-image of R will be omega itself, right? Because it contains -1. So in the pre-image you have 1. You can also have 3. For 1 you get that. So if you take the union of 2, so that will be omega, and omega is an element of F. So that case already works, right? Now, if you take A to be less than -1, okay, let's say if A is equal to R, the pre-image of R will be omega itself, which is an element of F. Because see, omega is an element of F. Now, if A is less than -1, the pre-image of A will be the empty set, because there will be no, because look, if A is -infinity, sorry, less than -1, so it means that neither -1 nor 1 will be here. So the pre-image will be empty. There will be no element that will map into that. So it will be the empty set. But the empty set is already there, so it's also inside. Right? Now, if A is greater than -1, but less than 1, if A is greater than -1, but less than or equal to 1, Because even if it's equal to 1, you put 1 there, it will not take this, right? But greater than -1 means that -1 will be included. So in that case, if -1 is an element, you take the pre-image, it will give you 1, 3. So in that case, the pre-image of A will be 1, 3. Is 1, 3 there? Yes, it is in F. Right? Now, similarly, we can target the case where A, in our A, it will only contain 1. Now, if we take A greater than 1, so from -infinity to A, which is greater than 1, contains contains 1. So if it contains 1, the pre-image will be 2, 4. So in this case, the pre-image of A will be the set 2 to 4. 2, 4. Is 2, 4 in F? Yes, this is 2, 4 is there. So it's also in F. Right. Now, if A is strictly greater than 1, or let's say greater than or equal, no, but what did I even write? Okay, if it's strictly greater, so you mean that it contains 1. Yeah, that's all. I've cleared all the cases. So we have all these cases, 1, 2, 3, 4. So all those cases are already there. So you see that in any case, the pre-image of A will still be in F. Therefore, we can conclude that F is measurable. Okay, I hope this will give you an idea on how to solve this kind of problem. So I think I'll stop here for today. I also hope that this will motivate you to learn more, right? They are really simple, just like algebraic manipulation, and also awakens your brain, this type of problem, to reason. It's a bit of reasoning and the like. Okay, I hope you will enjoy this session and that it will really challenge you and motivate you for more research. Okay. Thank you for your time. God bless you and see you next time. Bye-bye.